As you can see, I squeeze a lot of buzzword into my titles just to do you guys here. I think the objective has been achieved. So before starting, I want to see how many developers are doing Android apps. Are the rest of you guys iOS developers? Not really. Okay, cool. So today, with this talk, I want to achieve a very simple objective to show you guys the state of art for machine learning frameworks for mobile development, and also some personal experience and personal feedbacks. For the last 2 years, I've been working on a side project with this kind of frameworks. Okay, so before jumping into the real subjects, I want to record something which you guys are all very familiar with. So it's cloud intelligence. Traditionally, all the heavy operations of machine learning used to be run on the servers on backend. As a mobile developers, we're very used to just call an APIs and get the result we needed. So that's how we've been doing things for the last few years to make our apps smarter. You probably know Google Cloud APIs. You probably also know Amazon Web Services. They almost have the same panel of offers to achieve similar things. But today we want to focus on the on-device intelligence. So what's that? That is to run the machine learning models on the mobile devices directly, instead of doing network calls, instead of sending data to the server side. So why myself is really interested in this subject, because I think it provides a supplementary layer for privacy problems. So instead of sending users' data to server side, we can just doing everything, doing all the calculation, operation on device, on the edge. Everybody knows Moore's law. It has been successfully predicting the hardware developments for almost 4 decades. A lot of people say that Moore's law has already died. But actually, Apple released the A12 processor this year, which is a 7 nanometers processor. It's, again, making the performance jump a little bit. So we have reasons to believe that all this hardware advancement allows us today to do more and more machine learning on devices. At the WWDC 2016, Apple actually used the word on-device intelligence to emphasize their efforts of doing machine learning, apply machine learning on the OS level for their applications. For example, for iMessage, for calendar, and for photos. Android, at the same time, they're also doing their efforts. One of the most original and simple example is the conversation model, which runs on Android Wear 2.0. It predicts the response you can have according to the incoming message. Now it's being applied in everywhere. I think for the recent Gmails, you guys can see you can use the tab to complete your sentence. So all of this are thanks to the conversation model they've been training. At the same time, a lot of hardware companies has also been working on chips to optimize the machine learning operation. For example, Qualcomm, they have digital signal processor chips, which allows to optimize the TensorFlow operations. So comparing to a traditional CPU, DSP can actually run things 10 times faster. So as an introduction, the ultimate goals of all the machine learning on device is to make your mobile device even smarter than before. It's like giving them eyes and ears. So this is my own illustration, not very awesome. Consider all the benefits you can get by making your device a smarter one, considering some visually impaired people or other disabled people. By having this kind of functionality, thanks to machine learning, we can actually help more people. We can actually do more awesome things. That's my motivation. So I handpicked several very important events for the last 2 years to give you guys an idea of how everything has been advancing. So animation goes again. Starting from the original TensorFlow release, then we have mobile vision APIs for Android. Then we also have starting to have different speech APIs for iOS. Then we first have TensorFlow Mobile. so which they released this, 2 demos for Android and iOS in September 2016. Then we have the announce of TensorFlow Lite during the Google I/O of 2017. We have MobileNets, which is a model optimized for machine learning on mobile devices. Then we had Core ML 2. We also have the ML kit, which is announced this year. So as you can see, the effort has been very constant for the last 2 years. And for me, since I'm an Android developer on daily basis, what motivated me to try is the day that TensorFlow released the Android apps. Android demo, actually. So I checked out the demo that day, and I tried to compile it. At the time, it was still built with Bazel. So Bazel is one of the tools Google used to build their internal projects. So the build took around 20 minutes. The first result was the demo actually was able to recognize some common daily objects. For example, the beer bottle, the joysticks at our office. I was pretty psyched at this moment. I was saying, oh my God, we can do so much cool things with it. Because it's just a model like running offline on your mobile devices. So I started to get really excited. I started to talk to people, hey, let's do something together, maybe a side project, a small project. So we had some beer. We were saying, let's do some like educational projects. Because me as a foreigner, because I'm originally from China, I've been living in France for 10 years. My first year in France was miserable because basically I can't pronounce like daily objects. For example, fruits name, vegetables name, those common objects. So I was saying, what if there's a mobile apps which helps people to just learn the name of the daily objects? So that's the idea of making a small prototype to see how things works. The app is really, really simple, so you can just choose the language you want to learn and launch the app. Then app just scans different objects and says the name of the objects. So that's nice. That's the ideas to begin with. But then I realized there's not actually models for everything. There are generic models like Inception v3 and Inception v5, but they only works for a certain limit amount of objects, and they have a limited level of precision. So you can actually tell from an apple from a mango from time to time. So it needs some further training on those kind of models. So in order to build something really works for us, we have to train our own models. So that was the time I started to put my hands into the TensorFlow. I was saying, now you have to understand it and to see how it works. So today I want to give you guys a really general introduction about neural network. So how many of you guys here already know neural network? Okay, that's good, very fair amount. So here's a neuron, just like neuron in our head, but it's our artificial neuron. The artificial neurons has synapses too. So the synapses, they actually have different weight. Once they have a certain type of input, they can do some functions, then produce an output. You can consider the weight as a list of vector, so the vector with a certain direction. With certain input, then you can actually produce certain output. So here's a neural network, really simplified with only 3 layers. If we're giving out an apple, we're gonna feed the apple, so the bitmap, pixel by pixel, to the neural network. Then the neural network will be able to predict it's an apple, then a banana. So it's like, I'm confident it's an apple, not a banana. Google has been using cat and dogs as examples. That's how neural net works in a really, really simple way. But how do we actually train a model? How do we actually train a neural network to work in the purpose of our project? So actually, we should use a way called propagation. So how does backpropagation works? First, we will have a neural network. All the weights on these synapses are initialized randomly. We're going to feed some images to the neural network. Of course, since it's a randomly initialized neural network, it won't be able to predict the object like correctly. So it would say, I don't think it's an apple, I think it's something else. So that's how we learn from the errors. So we're gonna just tell the neural network, no, it's actually an apple. You should update your weights comparing to the result. So that's how we do the back propagation to update the weight of our synapses. Then the next time, So then the next time we feed some images to the neural network, it can function properly. So it will be able to recognize an apple from a banana, something like that. That's a very, very simple introduction of neural network. Today we talk a lot about a deep convolutional network, which means the neural network has a lot of layers. This is the architecture, the visualization of Inception v3 from Google. So as you can see, there's a lot of hidden layers. Different layers does different jobs. So for example, there are layers start by recognizing edges of an object. There are layers doing recognition of shapes. Then it goes to higher level functions. At the end, it's the classification of an object. If I give an example with an image of a sheep, that's how it works. But those kind of models are produced with a high amount of images and also long time of training. For example, Inception v3 has been training on millions of images collected by Google. And they also need like huge calculation powers, maybe a lot of GPUs to do that. We as Android or iOS developer, if we want just to have fun with the project, we normally don't have that kind of resource to do that. So what we do generally is called transfer learning. So instead of retrain the whole neural network, we're gonna keep all the weights in these layers. We're just gonna retrain the last layer, which is the classification layer. In that way, our model will be able to recognize the object thanks to the model, which is already trained on other images. So at that moment, I was ready to build something. So I had my first model ready. So several nights later, I started to configure Python first. So if you've ever considered configured Python on some Unix or Linux computer, you will see how complicated it can be. So my recommendation is to use some virtual env, so to separate your TensorFlow environment than others. Once my Python environment is ready and TensorFlow is installed, I start to collect images. So there's ImageNet. There are also, you can just crawling images from Google. Once I gather all the training data, I start to using very simple script to retrain my model. So this is actually some examples from TensorFlow for Poets, which is a code lab, one of the best code lab I think Google has to offer for someone who have never done machine learning and training before. The first time I trained my model, I used some random parameters. I end up with this kind of a TensorBoard. So TensorBoard is a tool to help you visualize the training process. I showed this TensorBoard to one of my coworkers who is a data scientist. He was like, oh, your model is overfitting. So what is overfitting? Sorry. So as you can see, the accuracy for the training data, which is orange, it's getting almost perfect, but my validation data, which is my test set, is actually still wandering around at the same level. At the same time, there's a cross entropy. So the cross entropy is actually a loss function, which helps to evaluate the level of precision of a classification model. I think I lost nobody here. Everybody is still with me. So the better the model is, the cross entropy, the lower the cross entropy is. So as you can see, the cross entropy is really low for my training set, but for my validation set, it's still very high. So in that case, actually my model is working really well for my training set, but not for my validation set. So that's not a good model for real life situation. So I have to readjust all the parameters. The second time I train, my model performs really better. So that was a happy face. At that moment, I obtained two outputs from my training. One of is the frozen graph. So it's a protobuf files for the model. The models actually stored all the weights I've talked in the previous slide. Then there's also a label file. So the label file actually contains all the objects the model is able to recognize. I dropped these files into the Android demo. So I started to build my first version of the Magritte app. But the first thing I noticed is the application size was huge. So it's almost 80 mega. So 80 mega is not acceptable for a mobile app. That's something not very cool about it. So I started to try to understand what's happening, why the app is so huge. So actually the model size is huge. The model is almost 80 mega. As you can see, this is a very huge neural network. So all the weights has been stored as it is. So which means are 32-bit floats. That's why the model is really, really heavy, like 80 megas. There's a way of reducing the model size. So the most simple way is do a quantization on the precision of the weights. So instead of having 6.4231 all the way to the 12th digit, we can just happy with the 6.42. So that's how we reduce in a first step our model size. So by doing the quantization after the training, we can actually reduce the model size to 4 times smaller. So that's the moment I started my first demo.
Let's learn to say the name of some fruits.
It takes a really long time.
Apple.
Like 3 or 4 seconds.
Banana. Kiwi.
So that's the first try, which I implemented the app at the beginning of 2017. I was not very happy about it because I think it's still too long, but I still have maybe things to improve. That runs on a Nexus 5X, I think. So I did some benchmark on the CPU and memory usage. As you can see, it's kind of really using a lot of resources, and my device started to like really burn at after some time. Just several months later, I think it's in June 2017, Google released the MobileNet, which is a machine learning model optimized for mobile platforms. At this time, they were showing some really awesome results. Comparing, according to the article, they're actually reducing model size with some dramatic changes. So at the time, I was like, this is very cool, and I should definitely try again with my app and with my models. So actually, it's very simple to optimize for your mobile. You just have to specify the architecture you want to use. In my case, it was MobileNet, and this 0.5 is a parameter, so that means I only use half of the layers, half of the weight. And image size. I almost use the same script. After some retrain, my demo works better. I was in a supermarket. So it's significantly faster. Banana is like French, but it's the same in banana. I also did some more benchmarks on the performance of the app and the resource usage. So as you can see, if I take all the weights, I use a lot of memory. Then if I take less weights, my memory usage starts to drop. The demo you saw, I used the MobileNet, which only used 20% of the original weights. So the precision didn't drop much, but the latency and the speed of recognition actually drastically improved. So that gives me a lot of encouragement in terms of prototyping and everything. Later on, Google did some other model optimization, and they start to show some comparisons. So actually, the quantization actually can save you maybe 4 times model size. And in terms of latency, it's significant. It's also very faster. For MobileNets, there's some accuracy drop, but not that much. And for inception, it's almost the same. Under the hood of an mobile Android application, so it's very simple. So basically, we took an image from the camera preview, then we do a central crop and resize it to make it the same size as the image you used for the training. And as for the architecture, it's very simple to understand for any Android developer. So there's a lot of mathematical calculation going on, but nothing is very too complicated. But for now, the mobile TensorFlow Mobile is already deprecated. The replacement is TensorFlow Lite. So at the time, there's not yet MLKit. What I have to do is I build a small backend which dispenses the model. And what my application does is to retrieve the models and the label file from the server and store them locally and use them. So that was my first try to showcase what we can do with machine learning models running on devices. 1 year after this year, during Google I/O, Google is releasing MLKit. So that basically undo everything I just did. So the model dispensing architecture you saw, it's natively supported by MLKit, so the model hosting. So where does MLKit situated on the whole Google machine learning product spectrum? So you see all the cloud API here. You see TensorFlow and cloud machine learning engines here. And MLKit actually contains both capacities. There's part of the MLKit are the cloud APIs. There are part of the MLKit are doing on-devices intelligences. So what Google did was to deprecate mobile vision API. They always do that. Then they took the products from Google Cloud Vision API. It becomes the Vision API inside MLKit. Then for the custom model part, they took the TensorFlow Lite, so as a backend of the MLKit. And they also use the Android neural network API. So since the release, I started to do some other tries with the Vision APIs. If you have already worked with a mobile Vision API, it's almost the same thing. It contains text recognition, which they are using now some really unified interface. The result is some blocks containing lines containing words. Face recognition, it's almost the same as before. You can identify different landmarks on one's face. For example, left eye, right eye, nose, mouth. If the person is happy, if a person is sad. Just like before. So last year, we did some fun project with mobile vision. So we're actually taking photos of people, then adding some accessories. So MLKit is just doing the same. There are also barcode scanning, and the new one inside the Vision API, it's called object recognition. So the object recognition, it's called image labeling, so it's actually very interesting. How does it work? It actually tells you what's the label, what's the object you can recognize inside of environment with a confidence, and also an entity ID, which is used by the Google Graph API. As for last but not least, there's a landscape API, which I haven't tried it out yet. But among all the APIs of MLKit, it's the custom model which interests me. Because simply it does the model hosting. For me, it's very essential for a mobile application because we don't want to bundle all the model files directly in our app. We want to be able to fetch them from a remote, and we want to be able to update them over the air. So MLKit really provoked me and make me want to try to see if the framework does better than TensorFlow Lite. So I start to check out how everything works. Basically, you have to still train your model if you want to use the custom model inside MLKit. Then you have to convert your model to TensorFlow Lite format. That's how things get complicated because Google is always very anxious about their new products, and the converter of TensorFlow Lite has been breaking for a while. They recently fixed it, but only for TensorFlow starting from 1.9. So before 1.9, the TensorFlow converter is still broken. They support 3 types of models. So frozen graph, a saved model, or Keras model. So Keras is a high-level API which you can use to train your model. Once you have a TensorFlow Lite model ready, you can host them on Firebase. It's as simple as uploading any files. So you just open the console and add your model. Then you can use your model inside your mobile application. I was like, yeah, it's very simple. Let's give it a try and see how things works. So I was stuck for a while, just doing the converts. As you can see, I used Bazel again because the TensorFlow converter was just broken. So the TO was the TensorFlow converter at the time. Actually, the script of converting is very simple. Everybody can do it without problem. You just tell them what's your input, what's your output, what's the inference type. So here I'm demonstrating a float model as an example. As you can see here, the input shape, the one actually means I have one batch of image. 2025 is the size of my image, height and weight. The 3 means I have 3 channel in my image because it's a RGB image. So they've been recently fixed the TensorFlow converter. So the converter now can do much more things. For example, it can convert graph def file or other files. It also works with the quantized model because the formal version doesn't. So after all these kind of troubles, I finally managed to generate my TensorFlow Lite model. So as you can see, it's almost the same as before, except it's a flat buffer format. The TensorFlow Mobile used to use a prototype buffer. So Google actually replaced with something even more compact. As for the upload, it's just fairly simple. Name your model, upload it, everything is done. Then it all happens in the code you have to write in your application. The Firebase model interpreter, it takes some input and it generates output. So MLKit for you guys, it's just like a black box. Give something as input, get something as output. So I'm going to showcase some of the code I write to make things work. First is the configuration. You guys can find the same parameters we use for the converting, for the training. Then we have to create a local model source. So the local model source declare what's the fallback of your model. And you can also declare the cloud source. So the thing about the model registration for MLKit is you can choose only to use a cloud model, so you don't have fallback. If the user don't have internet when he launched the app, there's no model. There's no feature. So MLKit, what they did do was adding a local model source, which helps for the fallback. Then we can just declare an interpreter. So the interpreter is the central of the custom model classification. As for the input and output, it's a little bit more complicated. It's mostly mathematics stuff. So the simplest way is to check out Google's MLKit demo, which is not the highest quality demo, but it works to understand them. So here is an example for the float model type. And the most important thing the demo does is to normalize the bitmap into some float arrays. So taking, for example, a photo of a kiwi, then we will have a byte buffer which is normalized. Then we feed it to the MLKit. Then MLKit will run the inferences on device, and we will get some result as output. So the code has been presented really fast. I just want to show you graphically how does that works. So actually you will obtain a list of probabilities. And the probabilities, the orders has been corresponding with your labels order. So what you can do is mapping your labels to get the result of the probability for each label. Then you can say, oh, here I have the grapes, which is the most confident. That's how we define what's the result of the recognition. After launching the demo, I also did some benchmarks on the performance. So actually, with TensorFlow Lite, the usage of CPU and memory has drastically dropped. So this one is the performance running with only TensorFlow Lite without MLKit. This one is without MLKit. We can see a little bit loss in terms of performance, which is normal because the SDK contains a lot more stuff. So we should do a demo live. Not always the best idea because live demo never works. So what I want to do is just a simple, I'll just pull out some images from my computer. So that's a banana. And he apparently struggling between apples and grapes. But as you can see on a device like Samsung S8, it's almost instant. So there's basically no latency at all in that case. So let's get back to the slide. Just to show you guys that with very small effort, using all the toolings, all the toolbox Google has provided, we can actually do a lot of things with it. The performance is really very, very advanced. We don't have to do much things to make things work. But what's next? So as you can see, TensorFlow Mobile has been deprecated. So now TensorFlow Lite is the default solution for all the mobile-related machine learning. And they've been optimizing the performance in various ways. And they are also starting to support wide range of different formats. For example, as you can see, the phrase, the graph, the safety model, and the Keras model. And they also recently released a MobileNet V2. So the V2 comparing to V1, which was about a year ago, it has, again, a huge jump of performance. And it's part of the TensorFlow Slim APIs. They're actually creating shortcuts between different bottlenecks. Bottlenecks is like a condensed layer in the neural network. And the result is really promising, but it's not yet available for some tests. As for the ML kit, the current state is it's still in beta. So 2 months ago, I implemented the first demo I did. Then 2 months later, the API has already changed 3 times. There's currently no any callbacks or feedbacks to let you know the model downloading is finished. So basically, you just have to guess the model is there and ready. Otherwise, you have to really put your local model source to make sure that your application can start and run right after the launch. And at the time of speaking, there is still lack of documentation in general, because there's a lot of concepts which are not native or natural for mobile developers, and we need maybe more context or like even like simple explanation to understand. There's still slight performance losses, but Google has been making an effort on that, so don't hesitate to open GitHub issues or try their demos. That's how we can make things progress and advance. But the best is yet to come. So during the I.O., they also announced the face contour, which will provide 100 data points, which allows, I think, developers to do other kind of features. There's smart reply, which will be soon available in MLKit, also with the online model comparison. So this is currently in beta, so some of us already got the invitation to try it out and giving feedbacks. Something more interesting to come. It's a paper they released last year on Federate Learning. So that's actually a way to improve your model. So with MLKit, what we can do already is by using some A/B testing to test our model in different ways. For example, I want to compare the performance of 2 models, so I'm just doing A/B testing and let some data to tell which model performs better. And with Federate Learning, we can actually uploading the incremental part comparing to the current model. So in paper, the Federate Learning only needs the incremental part of the model. So they don't actually need the raw data, which can be users images, users' photos. So if that can be turned into reality, I think it will be really cool for the community to build a new type of applications and softwares. So that's all for my talk. Thank you very much. So I have two projects. First one is kind of deprecated because you use TensorFlow Mobile. The second one is the one I just showcased. I think it broken down last night on the face recognition part, but the custom model part works. So Google provided an example with the quantized model. Mine works with the float model. And don't hesitate if you guys want to. Yes, questions? Yes.
Basically, how many different things can model from MLKit recognize? The model which you put on the phone directly, because I have used this default model from MLKit, and I was quite disappointed because it was very poor.
Exactly. So the default model you use from MLKit is a MobileNet V1, I think. So it's a generic model. I think it can recognize more than 1,000 objects, but with a really low precision. I think it's around 65%.
Yeah, I think it was only like 400 things, so it's not enough.
Yes, it's not enough. That's why we need specific models.
And how much things can such a custom model recognize at max to be reasonable? To have an upsize, I don't know, 50 mega and no more, and
there's actually no limit.
What do you think?
It can go with like maybe 1,000, maybe 10,000 category labels of image, but that will surely augment your size of model. But like in theory, you can go really a lot of labels, and you can also do model stacking. So which means you can stack different classification, but combine them in the same model. That's something I didn't really understand how it works, but model stacking, you can check it out.
Okay, thank you very much. That was a great talk.
Let's say you have like a recipe written in text, like, I don't know, apple, flour, lemons, whatever. And say you have a database of like whole food products. How can you recognize, for example, putting a camera onto the recipe and just to map it on your database objects?
I'm not sure I get the question 100%.
For example, my camera sees the word, not the image apple, and I want to map it on the apple object from my database. Like,
okay, that depends on, for example, first, if it's printed text, it works better, because if it's a handwriting text, it's gonna work really, So it's printed, then you just have to be able to extract the text. Then what you can do is like solely depend on your capacity of coding, I think, Because what Google, the SDK does is just to give you the blocks which contains lines, which contains words. I can do a live demo as long as the things is still here. I don't know if there's, so if I catch this one, I have a text recognition going on. So as you can see, I can recognize everything written here. Since this demo is using a camera preview in live, so basically it's just keep refreshing.
So but you can get every single word?
Yes.
Oh, okay, great.
Yes, but it's up to you to sort it out. I think that's something extra you have to do with the SDK.
Okay, thanks.
Thank you very much.